All right, we're going to look at 16.7, which is weak bases, and then 16.8, which deals with the relationship between Ka and Kb. Okay, when we look at weak bases, here we're abstracting protons from water, and we're making some OH minus. So we're also going to form the conjugate acid of that base. Okay, so for example now, if I have a base, we're going to choose B for base, and I add that to water. Remember, water can act as an acid or a base, so now we're going to have water acting as an acid. So B is going to take the H from water, make HB plus, and then we're going to have the leftover OH minus from the water. So if you have something like NH3, which is a base, NH3 with water, okay, it's going to take and make NH4 plus, because it's going to take one of these protons or hydrogens from water, and then we're left with OH minus. Even though we have pluses and minuses, notice how they do add up to be 0, and we don't have any charge on the left side. If you see a Kb, that is the base dissociation constant, and that means now we're looking at this from the angle of something as a base versus something as an acid. So as the acid falling apart into its parts of H plus and Cl minus. Now we're looking at the Cl minus gaining and making H plus. So it depends on which way you're looking at, whether you're talking about a Ka or a Kb. And when we look on the right side in that chart that you have on your notes, notice how all of them do have the OH minuses on the right side and something plus. We're looking at it from the viewpoint of the base if you're dealing with a Kb. Okay, so let's calculate the concentration of OH minus in a solution of 0.15 molar NH3. So if I'm dealing with NH3, now we're looking at it from the viewpoint of the base, so NH3 in water. Before we kind of just got rid of water and didn't think about it. Here it's a little easier with the bases to actually write water in, but you don't have to. We're going to have NH4 plus and OH minus. Now we can't just go the POH in that route because NH3 is not a strong base, but a weak base. So we're going to have a little bit of equilibrium here. NH3 initially is 0.15. Water I don't care about. I don't have any of these to start with, so it means I have to shift to the right. So we're going to have plus X, and I'm going to have 0.15 minus X. So then we do the what we were looking at before, which is the Kb is the products over reactants. We're going to have X squared all over 0.15 minus X. Our Kb is going to be a small number, so I can actually get rid of that. When we look up our Kb in the back in Appendix D, and I'll tell us that it is 1.8 times 10 to the negative fifth. All we do is cross multiply, take the square root, and my X is 1.6 times 10 to the negative third, and that is my OH minus concentration because X is just the OH minus. And that is all that question is looking for. Okay, there are two types of weak bases. Okay, the first one is the non-bonding pair of electrons serve as my proton acceptor. These are usually nitrogen molecules. So if something has a free set of lone pairs, that free set of lone pairs can serve as a spot to then take a proton. So a lot of times nitrogen has a lone pair, so an H plus can come right along and attach to that because H doesn't have any electrons, nitrogen has two to kind of spare, so they're going to end up sharing, and then you're going to have the bond there. So that's the first type of weak base. The second type of weak base are the anions of weak acids. So ClO minus is a weak base because it is the other end of HClO. Okay, so you'll see these as bases because they can take a proton and be HClO, or I can see things that are usually nitrogen molecules that have lone pairs that'll then take an H that is free and around in my solution. Okay, for 16.8, we're looking at then the relationship between Ka and Kb. And when we're looking at Ka, we're talking about the acid dissociation constant. When we're dealing with Kb, we're talking about the base dissociation constant. Okay, well, what we're going to notice here is that if I have a Ka, which is for HNO3, I have a strong acid, so that Ka is going to be really, really, really large. That means the base, NO3 minus, is a very, very weak base, so it's kind of negligible. Well, if I have a weak acid here in HF, F minus then is a little bit stronger, or a little bit weaker as well. So if I have a weaker acid, but a strong weak acid, and 10 to the negative fourth, that means I'm going to have a fairly weak conjugate base, which my Kb here is very small. So one goes up, the other goes down. As my Ka increases, my Kb decreases. Okay. So if you have a Ka that is large, I'm going to have a strong weak acid. That means the other end is going to be a weak conjugate base, or a weak conjugate base. If you have a weak acid, then that means I'm going to have a strong weak conjugate base, which means I'm going to have a large Kb. Whereas the stronger one here, I'm going to have a large Ka, or larger when we're talking about strong, weaker ones. Well, Ka times Kb is going to be Kw, and this is on your green sheet, which then also means that the pKa plus a pKb is going to be 14, because that is my pKw. All you did was you went through and took a negative log of everything, okay, and you changed it to a plus instead of a multiplication. But this Ka times Kb equals Kw, that is on your green sheet, okay? So let's try the one practice problem we have here. Calculate the base dissociation constant Kb for the fluoride ion F-. So fluoride, okay, F- is the conjugate base, or is the other base end of HF. So here's my base, there's its conjugate acid. So I look up HF in Appendix D, and it'll tell me that the Ka for HF is 6.8 times 10 to the negative fourth. That means that the Kw is 1 times the other. So 1 times 10 to the negative 14th is going to be equal to 6.8 times 10 to the negative fourth times my Kb. So all you do is divide. My Kb is 1.47 times 10 to the negative 11th. You will often get Kas. You will very rarely get Kbs unless you're dealing with a common Kb like ammonia, NH3. You will more often get a Ka and have to convert it to Kb if you're talking about it in terms of the base.